We're going to take a look at mathematical induction. And first, let's get started with the principle of mathematical induction. So what mathematical induction says is that assume that we have an infinite sequence of mathematical statement. That's, for example, like P1, P2, P3, P4, blah, 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 goes on forever. So we call it like an infinite sequence of mathematical statement. To prove that to prove this whole statement is true, two conditions needs to be met. The first one is that if P1 is true, which is what we call the base case in an induction. And the second case is that for any natural number k, pk must implies pk plus 1. So what exactly does this condition mean? Well, the first one is easy to understand, is that we have to prove the first case or the base case is true. But what exactly does this mean, right? Well, this ensures that there's connection between each one of the statement. For example, this P1, P2, P3, P4 statement here, right? So what this says, that this proves that there's a connection, that P2 implies P3 and that P3 implies P4. That it ensures that there's a connection between each one of the statements in this sequence, right? So what mathematical induction says is that if we can prove these two are met, these two conditions are both met, then we can say that all of the statement in this infinite sequence of mathematical statement is all true. So how exactly is this useful? Well, let's take a look at an example, right? Well, our proof here is that we want to prove for any natural number n, we have 1 plus 3 plus 5 blah 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 plus 2n minus 1 is equal to n squared. So what this is that we start from 1 and the sum of them, 1 plus 3, because you can see that 1, 3, 5, they're all odd numbers. We'll say that the sum of two or multiple odd number will always result in a even number. That's what we want to prove, right? Well, you can say that we can prove, well, the base case in this case will be, of course, 1 plus 1 itself being, let's write it, P1 in this case, right? So what will P1 be? P1 will just be 1 is equal to 1 squared. So this is a check. You see, the base case in this case is met. So the base condition is met. And we can also see P2. What does P2 look like? Well, P2 looks like 1 plus 3 is equal to 4. And 4 is 2 squared. And this is met. Makes sense, right? What about P3? 1 plus 3 plus 5, which is equal to 9. Which this is essentially 3 squared, right? We can see that. We can just go on to prove P4, P5, P6, go on to keep writing it like this. But the problem you're going to meet is that there's an infinite number of natural number n, right? So you cannot just write down each case of them. So you got to have a way of proving to show that this infinite sequence of mathematical statement is true. And to do that, we use our methods, which is so-called induction, where we make sure the base case is true. Well, in this case, it is true, right? Because 1 is equal to 1 squared. And then we need to make sure that pk implies pk plus 1, which that part ensures that there's connection between each one of the mathematical statement. So a lot of people like to use like dominoes as like analogy, right? Like if you line up dominoes in a straight line, like then pushing the first domino to create a chain effect that eventually brings down all the dominoes. However, to make the whole domino thing work, right, two good conditions must be met. The first condition is that there must be a push to the first domino, which in this case will be an analogy to the base case, right? We gotta make sure the base case is true. And the second, that you gotta ensure that there's connection between each dominoes. So not that like if the dominoes, let's say, are placed too far away from each other, if you push the one, right, the other one's not gonna fall. So to make sure that they all fall, you have to make sure that they're close enough. In this case, is the condition 2, which is that there's connection between each one of the mathematical statements. So let's look at our example here. How exactly are we down to prove this? Well, let's actually erase P2, P3 first, because we don't actually need that. Well, our first step into induction will be really easy, which is checking the first condition. Is the base case true? Well, the base case is 1, right? 1 is equal to 1 squared. So it definitely, the base case P1 is true. So now comes the harder part, which we call the induction step, or the induction. You gotta have like an induction hypothesis. So right. So let's rewrite condition 2 to make this more clear. So we need to prove that for any natural number k, pk implies pk plus 1, right? In other words, we assume that this is true. 1 plus 3 plus 5 blah 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 plus 2k plus 2k minus 1, not plus 1. 2k minus 1 is equal to k squared. This is what we so call our induction hypothesis. And then we need to prove that 1 plus 5 blah 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 plus 2. Now k is replaced with k plus 1. Minus 1 is equal to k plus 1 squared, right? So this is what we're trying to prove. We're trying to prove that there's logical connection between these two statements. So now let's look at our statement right here, and you can see that what is this. So let's look at this part specifically. So this part says that 2k plus 1 minus 1. So 2k plus 1 minus 1. So what is this? Well, this is essentially 2k plus 2 minus 1, which is what? Which is 2k plus 2 minus 1, which is plus 1. So we know that each individual number in here, in the sequence, is a odd number, right? So if it's 2k plus 1, what is the term before 2k plus 1? Well, obviously it's 2k minus 1, right? So it goes from 1, 3, 5, blah, 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 2k minus 1, 2k plus 1, right? It makes sense because then 2k is in between, and then these two are both odd number. So we first observe that this is essentially 2k plus 1. So the sequence now, this, if we know that there's the 2k minus 1 is the term before 2k plus 1, we can write it in terms of 1 plus 3 plus 5 blah 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 plus 2k minus 1, which is term before, plus 2k plus 1, right? Which is equal to k plus 1 squared, right? So as you can see, look at this part. If we isolate this part out from 1 plus 3 plus 5, from this part to this part, recall that at first we know that this is equal to k squared. This is our assumption that pk is true, right? We assume pk is true. Then we want to try to use the fact that we assume that pk is true to prove that pk plus 1 is true as well. So this is our initial induction hypothesis, right? So we know that this part is equal to k squared like we assume, and then we keep the rest the same, plus 2k plus 1 is equal to k plus 1 squared, right? And then you can see that this is indeed true because these two are indeed equal. So therefore our pk plus 1 is indeed true, if under the assumption of that pk is true, because we need to assume pk is true first, right? Because if by assuming that pk is true, we know that 1 plus 5 plus 1 plus 3 plus 5 plus 2k minus 1 is equal to k squared. We know that based on the assumption of that, then we show that pk plus 1 is true by all these algebraic manipulation and observation we made based on this specific case. And at the end, we successfully show that if we assume that pk is true, it indeed implies that it is equal to k plus 1 squared, which means that these two are equal, which means that our k plus 1 case is true. So we managed to prove pk plus 1 from pk, which completed the induction step of proof. So by the principle of mathematical induction, our equality 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared is valid for any natural number n. So that is the example of an induction. I'll make more example or in my next few videos, but the big idea of induction is like the same analogy as the dominoes, is that like a lot of times we cannot just write down all of the mathematical statement, right? We cannot just write down each one of them because you just can't. There's infinite of them. So what we try to do is that we try to make sure the first case, which is the base case, is true, and we make sure that there's connection between each individual statement. That's kind of a little bit misunderstanding, but you get what I mean. Is that you gotta make sure that there's connection, and you gotta prove that there's a base case that is true. And then we call this the method of mathematical induction, which we use to prove an infinite sequence of mathematical statement, right? So that'll be my intro on mathematical induction.